Hello and welcome back to Calculus 1, section 4.5 on optimization problems, meaning min and max. We want to find maximum profit, minimum cost, minimum distance to get somewhere, right? So we optimize because we are lazy, right? As a species, right? The lazier we are, it's just a fact of nature, actually. It's not just us. All things in the galaxy are trying to exist in a minimum energy state. All of it, which is why planet is a ball, all right? And if you believe it's flat, just go to the edge and jump off of it, please. Because we don't need that in a gene pool. All right. So what we have is optimization problem, and I would like to introduce this idea by, let's say, two numbers, say x and y, add to, let's say, 18. Find x and y such that their product is maximum. All right. So would we agree that if I add number 0 to number 18, we're going to get 18? Would we agree? We'll just make a guess. So if I add 0 plus 18, I will get 18. Now, what's 0 times 18? 0. Is 0. All right. Can we come up with another combination of numbers that adds to 18? And the next natural would be 1 plus 17, which is also 18. And now you have 1 times 17 is 17. Well, that's better, right? It's bigger than 0. And then you say, okay, well, let's try 2 plus 16, because that's also 18. And now 2 times 16 gives us 32. And that's even better. 3 plus 15 is also 18. 3 times 15 is?
45.
45. I know, class just started, so we're not there yet. 4 times 14 is 56. Do you see that as we are trying to guess this, the values of the product are constantly going up? Now, they are going to hit the maximum at some point, because if I am to reverse and say 14 plus 4 is also 18, I'm going to have 14 times 4, it's going to be 56. Actually, hold on. I need another one. So 5 plus 13 is 18. 5 times 13 is 65. And then we're going to have a whole bunch of these. But now if I say 14 plus 4, right, because I'm going from 0 all the way up to 18 and trying all of the combinations, right, for whole numbers, I'm getting over here that 14 times 4 is 56. But look, that was 65. So somewhere in here are the two numbers that give max product. And the question is, how do we find it? Now, what I'm going to show here goes for all word problems in the entire section. You have two sentences. You will create two equations. You will combine equations, take the derivative, and win. Now, let's see. First sentence says the two numbers add to 18. Way to translate that mathematically is x plus y is equal to 18. The second sentence that I proposed is that the product of the two numbers is a maximum. xy is a max. So now these equations have names. The equation with the max in it is called the objective equation. Because you are trying to achieve maximum product. So that's objective. And the other equation is called constraint. Because would you agree that if I use numbers 50 and 10, the product will be bigger, right? But then 50 plus 10 is not 18, so that's a constraint. So equation without min and max in it is called a constraint, and equation with min and max is called objective. Because in some problems, they will say the objective equation, right? Some problems they will say with a constraint. So this terminology will pop up in certain problems. You need to know the names of these equations just in case. More of this, obviously, when you do these problems in 3D, in Calc 3. It's coming up for some of you. So what I have here is a system of two equations with three unknowns. And you go, oh, if I just had another one, right? Because we like three equations for three unknowns, four equations for four unknowns, right? And I have x, y, and max. I don't know any of those. Now, remember how I showed you the way to take to find the slope of a line having only one point, and you didn't react. You were not amazed, right? Well, now I'm going to show you how to solve all of this without the third equation, and let's see if you have a better reaction, okay? So, as in any other system of equations, we are going to use substitution to eliminate one of the variables. Maybe we should write that in blood. Use substitution method to eliminate one of the variables. So I am going to solve x plus y equal 18 for, let's say, y, and get 18 minus x. Now I'm going to plug that into the second equation, and I'm going to distribute and now I have an equation where I would like to find the x so that I get the maximum value on the other side. Now, how do we find maximum value of a function? We take the derivative of it. Now, remember what is the next step? When you take the derivative of the function, what is the next step to find min and max?
0.
You set it equal to 0. Now, do we all agree that the max is some kind of number? Like 100 or 500? What's the derivative of that?
0.
Is 0. Do you see how everything kind of clicks in right away? As soon as I take the derivative of this in respect to x, I'm going to get 18 minus 2x is equal to 0, because the derivative of max, which is a constant, is 0. Constant, it's some number. And look, x equals 9. We immediately found the number. So now I can go back into y equals 18 minus x and figure out that y is also equal to 9. So if these two numbers are the same, they will make the largest product, which is why square has the largest area if you have the rectangle. Well, you can figure the geometry of it now. So x equals y equals 9 will give largest product. And that product is 9 times 9 equals 81. So this is the way we do these problems. We read the problem, create two equations. Problems could be talking about geometry, they could be talking about cost analysis and profit analysis, a whole bunch of different applications. The principle is create two equations, plug one into another, eliminate one variable, take the derivative, it will immediately have a zero, and then just plow through the rest. So let's take a look at some of the problems that we usually see. The most frequent problem is what we call farmer's problem or farmer's dilemma. Farmer's problem. So on a farm, farmer wants to fence off an area for pasture or vegetable garden or orchard, doesn't matter, right? For something. So farmer has a rectangular plot of land and he has a set amount of fencing, 200 yards, 2,000 yards, whatever number we put. What are the dimensions of the largest, right? What are the dimensions of the largest area to fence off with the amount of fence that you have, that he has? So, farmer wants to fence off a rectangular plot of land of max area using 2,000 yard of fence. Find the dimensions. All right. Well, we draw the rectangle because we know rectangular plot of land. We have x and y values all around. We know that we have 2,000 yard of fence. Now, what is that piece of information? 2,000 yard of fence. What is it?
The perimeter.
It's the perimeter, because it's a perimeter fence, right? Right now, looking at that page, you are like a bird that it's flying over, and you're seeing this on the ground, and the black line is the fence, right? So, perimeter fence. So we have a perimeter equation, which is 2x plus 2y for the rectangle, is equal to 2,000 yard, and that's your constraint. Why is a constraint? Because all you have is 2,000 yard of fence, right? So it's a constraint. Then we have the maximum area. What would that be? xy equals max. Because we want the maximum area, maximum possible area. Now, if you divide upper equation by 2 to make the numbers smaller, we have x plus y equals 1,000 and xy equals a max. What's different between this problem and the previous problem we had? Right, the 1,000 actually was 18, right? It's the same thing. It's the same problem, the same variables, same everything. It's just that, 1,000 was 18 in the previous example. So we solve from the first equation. We solve for y, which is 1,000 minus x, and then we have x, 1,000 minus x equals a max. Right, when you plug in the second equation, it's 1,000x minus x squared equals a max, and then you hit it with the derivative. So that's going to be 1000 minus 2x equals 0. X equals 500 yard. And then y will also be 500 yard when you subtract from 1000. So max area with 500 by 500 yard dimensions. It's identical problem, right? It's just we replaced 18 with 1000. Now, this is something that you can do, right? And I am going to have a challenge problem for you, which leads into your project. You will be constructing the box of the maximum volume from a single sheet of printer paper such that you have the maximum volume and your box will have no top. Right? So I'll give more directions, but calculating and constructing that box is going to be the project, part of your project. That is due the final exam, so you have time, but you need to know I needed this lecture for it. So your project contains 3 word problems. A problem on related rates, a problem on this, and another problem in integration. So that's the 3 problems, and it's due the day of the final exam. So now, what I'm going to do is I'm going to modify Farmer's problem. Say there is a river. Right? How do we know it's river? It's blue. Because there's salmon in it. Look at that. So, wait, if the salmon goes to the right, which way the water flows? The answer is, depends on time of the year. Because one time of the year, salmon goes one way to mate, and then the other time of the year, it goes back where it came from. So next year, they can go again. I'm not sure why they do that, but do we have any biologists that can explain? No? All right. So now, farmer is going to put the plot of land here and not worry about fencing off area on the side of the river, because, right, you're going to put some animals in there, and right, yeah. They're not going to go swimming. I still have 2,000 yard of fence. What's the max area that you can fence off? Excellent. 2y plus x is equal to 2,000. xy equals the max. So now you know what to do. Solve the first equation for x, plug in a second equation, let's go. No pressure, I have 18 seconds, go. This is priceless. New Jersey essential oils started following me. Why is it make fun of that? Why? This has to be a bot. This is priceless. I even said in one of the classes, like, I don't know how you solve quadratic equation. Use the quadratic formula, do the factoring or essential oils. I don't care. Oh, this is amazing. Stay on this. All right, so again, more of the same. We're going to get different numbers. So from the first equation, we have that x is equal to 2000 minus 2. It doesn't matter if you solve for x or y. Just make it simple, okay? If you solve for y, you end up with fractions. If you solve for x, you don't. The result at the end will be the same. So now we're replacing x. So that's going to be 2000 minus 2y times y is equal to a max. And now we take the derivative d dy, right? Because it's a y variable that we're working on. Oh, hold on. I forgot to simplify. So 2000y minus 2y squared is equal to a max. Now I take the derivative. There we go. Much better. Because up here I have to do product rule, right? Yeah. So multiply it out. So we have 2000 minus 4y is equal to 0. Derivative of max, derivative of min, they're zeros because max and min are just some numbers, right? 500 square yard, right? It's just a number, 5,000, then you just, it's the derivative, is 0. So now y equals 500 yard. Now, before you scream, that was the same like previous one. When you calculate x, x is going to have a different value. X is 2000 minus 2 times 500, and that's going to be 1,000 yard. So now area, the dimensions are 1,000 for x times 500 by 500 yard, and these dimensions will produce max area. And this time around, you see that it's a rectangle, right? The previous example was 500 by 500. That was a square. Now it's 1,000 by 500. Well, that's a rectangle. Great. Now we can have, well, farmer can have all types of fun and configuration, right, with these problems. What if farmer wanted bins? right? Because you want to put cabbage, rabbits, and tigers right in each. You don't get to mix these, right? What happens if the rabbits and the cabbage, right? You get the idea of the tigers and rabbits, right? This is not going to be pretty. So you don't mix these, so we need 3 bins. Great. The entire length on the bottom, x. How many y's do you have? 4 y's. So you see your equations change, right? Your equations change depend on configuration that you have. Calculations will always stay the same. You always solve for x, you always solve either x or y, and you plug in another equation, hit it with the derivative, and then solve. So your job is to translate these words into, right, the geometry, the picture, and then you just go and solve the rest. So now we have 2x plus 4y is equal to 2,000 yard of fence, and we still want x times y to be max because we want to maximize the area. So now you divide the top by 2, thank you, to kill off the, at least to make everything, every number as half. So x plus 2y is equal to 1,000, and then x is equal to 1,000 minus 2y. Now this is different than the previous example because previous example was 2,000 minus 2y, now is 1,000 minus 2y, so it is different. We have 1,000 minus 2y times y equals a max, and 1,000y minus 2y squared equals a max, and then we hit this with a derivative in y, and we have 1,000 minus 4y equals a max, and here's your y, 250 yard. In this case, if y is 250, x is going to be 500 yard, and the dimensions are 500 by 250 yard for the max area. Does it make sense to be smaller? Of course, because you used a lot of fence for the middle, right? So of course it looks a bit smaller. And now just, you can let your imagination, go wild and figure out any type of situation there. Let's take a look at something else other than the garden. So we talked about do we have any packaging engineers in the house? Packaging engineering is one of the booming areas now. They, have to pack and ship a lot of stuff, and none of it's produced here. So it needs to arrive in one piece. So is it important to save 10 cents per box? Why? It's 10 cents. 10 cents for 5 million boxes. Yes, it's a significant amount. 100,000 boxes, it's still a significant amount, right? So you are hired at a company to literally save 2 cents or 5 cents of a material on a box design. And if you save 2 or 5 cents times 100,000 boxes, you are saving company a lot of money, right? And you are now you will see the calculation for something like that is a joke, right? So you will be working at the company, doing these kind of things, right? Making your 50, 60, 70K a year, doing exactly what this problem is going to work out. And all you're looking for is to save just a couple of cents, right? Now, what are you supposed to do? Well, the amount of material that you need to bend into making a box, right, is represented as a surface area of the box. So you are supposed to minimize surface area. So we are going to minimize surface area, and we are going to keep, let's say, volume fixed. Now, the problem that we are going to do is not going to cover, obviously, all cases, because if you are messing with the shape of the box and you are trying to ship the projector, well, the box has to have a certain shape, right? So you don't have a lot of room to play. But if you are shipping ping pong balls, they can, right, when you put them in a box, they will take the shape of the box, right? Because you're placing 100 ping pong balls in a box. Your box could be in the shape of a donut and it's still gonna work. I mean, so whatever shape fits, right? Whatever shape fits. So let's see, minimum surface area of the box. Of all boxes in a galaxy with a square base, guys, we need a square base in Calc 1. Calc 3, any base, okay? But in Calc 1, we need a square base because, remember, the box is a three-dimensional object, so x, y, and z, and that's 3 variables. And that's Calc 3. Now, if I have a square base, then the dimensions are x and x, and then a y for height. So now I have x and y, 2 dimensions, and we can deal with that in Calc 1. So the box that you will be making at home with a maximum volume, with a constraint. So you are doing technically backwards problem, right, from this one. Because what I'm going to do here is I'm going to minimize surface area with a fixed volume. At home, you will have a fixed surface area because you're given a paper, right? And you will try to find maximum volume. So it's kind of opposite of what we are doing in here. So minimum surface area, though, this is problem 19 in the textbook. So of all boxes with square base and the volume of 8 meters cubed, so volume V is 8 meters cubed. Which one has the minimum surface area? So find dimensions of the box. So if I draw the box, I have x, x, and a y. So we know that the volume is area of the base times the height. So volume is x squared, which is area of the base, is a square base, times the height, which is y. And that needs to be 8. Hello, constraint, right? X squared y equals 8 is a constraint. Now, what's the surface area? Well, how many sides do we have on a box? And what are the areas of each of those sides? Added together needs to be a min. So, how many areas do we have for a box? 6. Please look at the box you are sitting in. It's called a classroom. Right? You have a ceiling and a floor, that's 2. You have the green wall and a whiteboard, that's 2. You have the window and a door, right? Walls, so that's 2. 1, 2, 3, 4, 5, 6. So 6 boxes. What are the areas of top and the bottom in this case? X squared, good. So I have the area of top and area of the bottom. So area will be 2x squared, because I have x squared for the bottom, for the floor, and x squared for the ceiling, right? So 2 of those. And now I have 4 sides. Each side is xy, right? If you take a look at this over here, right? That's one of the 4 faces, and it's xy. So I have my area equation, and I want that to be minimum, because if I minimize the surface area, I minimize the amount of material being used, and I immediately minimize the cost of box production, right? Times the number of boxes, it's the savings across the board. So I have my 2 equations. X squared y equals 8, and 2x squared plus 4xy equals minimum. From here, I solve for y is equal to 8 over x squared, and plug in the second equation. As soon as you plow through geometry, the rest of the problem should be cruising, right? Solve for a variable. Clearly you don't want to solve for x squared, because then you're going to have square roots and all of that, right? So solve for y. There should be always either both are easy, or one is easier than the other. Should be obvious. So trying to grind through this calculation, when you plug in, simplify, hit it with the derivative. Do we all have 2 by 2 by 2? Excellent. Excellent. Okay. If we minimize the distance, we don't have to go as far, right? So let's see, closest point on a line, 22. It says what point on the line, what point, meaning xy, right, on y equals 3x plus 4 is closest to the origin. Now, geometrically, we go 1, 2, 3, 4, then 1, 2, 3 up and 1 over, so it's a line something like this, going through 4, and perpendicular, this would be our distance d, that's the origin 0, 0, and this over there is the mysterious xy point. It's perpendicular distance to the line that it's the closest to 0, 0. Would something like this be even remotely important in designing a GPS, let's say? Of course it would, right? So what do we have? Well, we clearly have a constraint equation y equals 3x plus 4. That's already given to us, right? There's constraint is that you can say y minus 3x equals 4. Whatever, so that's already given. What would be the other equation? What would be the other concept? Right? Excellent, distance formula. And then also, the closest is which kind of concept? It's a concept for closest.
90 degrees.
No, the closest word. What are we trying to do? To find? Minimum. Closest is the minimum distance. So distance formula, and we're looking for the minimum because it's the closest. You could have gotten here through Holland Tunnel, right? It totally work. Take you 5 hours in this traffic, but right? So the distance formula here in blood, distance between 2 points is x2 minus x1 squared plus y2 minus y1 squared. So that's the distance formula between 2 points x1, y1, x2, y2. So now we say that the distance between mysterious x and 0 plus mysterious y and 0 needs to be minimum. So there they are. Objective equation with the minimum and constraint equation, the other one. So now I have that the distance is equal to square root of x squared plus y squared equals the minimum. Oh, I don't need the d. I need to... No! I need to plug in first. So we replace y. Let's go here. So distance is equal to square root of x squared plus, and now we have 3x plus 4 squared. That's going to be square root of x squared plus 9x squared plus 24x plus 16. Please don't forget that 24x is a, you're squaring binomial, so there is a middle term. 24x. It's also known as the grade slayer. So the distance formula now is the square root of 10x squared plus 24x plus 16 equals a minimum. We all see that this equation only has x's. So this is where we hit with the derivative in respect to x. So now the derivative of the square root, we don't have to worry about this d. So the derivative of the square root is the derivative of the square root divided by 2 times the square root. So the derivative under square root is 20x plus 24 divided by 2 times the square root as is, which is 10x squared plus 24x plus 16 equals 0. So now you cross multiply this, it will kill the square root, and you are left with 20x plus 24 equals 0. So x is negative 24 over 20. Cancel both by 4. You get negative 6 over 5. X is negative 6 over 5. Guys, that's a location. Does it make sense for it to be negative? Yeah, look at the picture. That's one negative x value there. And we are expecting what kind of y value? Positive y value, right? Because that's the way the picture goes. So y value is equal to 3x plus 4. So y is equal to 3x plus 4, which is negative 18 over 5 plus 20 over 5 equals to 2 over 5. So the xy location we are looking for is going to be negative 6 over 5, 2 over 5. That's the answer. How cool is this? On a scale 3.7 to 8.1. Nice, right?
Question on the derivative. Do you use linear? How do you derive that?
I memorized that the derivative. So the question is, how did I immediately solve the derivative this way? What I memorized is that the derivative of square root of x is 1 over 2 root x. So this is what I memorized. And then I said the derivative of square root of f of x, now it doesn't matter if it's e to the x, log, sine, whatever, has to be f prime of x divided by 2 square root of f of x, because it has to follow the same form. So that's exactly what I have done. The f of x is the argument under the root. So we see that x is x over here. So f of x is f of x there. So they look the same, except when you have a function you have to follow by the chain. So this is the chain, and here is your f prime to root f. All the derivatives work that way, and I believe on your exam you guys had inverse cosecant, where your your function f was e to the x squared. So you enjoy that one. How about some business? Let's make some money. Who has money? Oil companies. Why? Because they have oil. So let's see. This is going to be a cost analysis. We're going just to throw some numbers out there. These are not real numbers. We can agree. Here's the picture. This line over here is the shore. So shore on this side and sea or ocean on this side. I don't care. Here be the oil rig, which is, say, 5 miles out into the sea. Whatever. 5 miles too much? Okay, fine. Use 2. Just because if you're writing with a pen,
Does it start at the break of the water, or does it start on the shore?
well, there is just. We're not going to worry about 10. We're not going to worry about 10 feet over there.
We're worried about 5 and 2.
Now, what I'm going to have is oil refinery over here. And the oil needs to get in there. So I'm going to have this black route for pipes. And since it's only 2 miles off the shore, I mean, to have a tanker ship going between the 2 locations, right? So just put some pipes, right? It goes directly. Now, there is also a pipe that we can do directly, right? Wouldn't that be much shorter? That's much shorter. Let's put over here, let's say 5 miles down the shore. We can calculate the value here, right? It's very simple. It's Pythagorean theorem. So square root of 2 squared plus 5 squared is equal to square root of 29. And square root of 29 is about 5 something. 5.3? I don't know. We use 1 decimal. So square root of 29, 5.385, lost my touch. So 5.39. No. So now, let's make up some prices. To lay pipes on the ground is much cheaper than to lay pipes under the water. Just think about it. You have to put them all the way down. It's a lot of pressure, right? You have to have divers, then you have to weld underwater, and it's just a lot of mess to put pipes underwater. For the ground, you just tighten some bolts, you're done, right? So it's much cheaper to install pipes across the land. And so what would be the cost of, but let's just make up some numbers. For a mile on a land, 200,000. Maybe that's low, but 200K for 1 mile. To put, you know, the power towers, the big ones, right, with the lines. One tower plus the lines on one end, because this tower belongs to the other end, is 100K. So now you just drive somewhere and see them, right? And any single one you see with the wires that belong to that one, it's 100K. So let's say, so cost, 1 mile ground, let's say 200K, and then 1 mile water, let's go with 500,000. It's more, but 500, whatever. We're making it up anyway. Now, do you see yourselves working at a company or contracting for a company to calculate whether we should run the pipes on the ground or whether we should run underwater? I mean, this part over here is underwater anyway, so this is a combination of the two. So now I have the black path, number 1, and the blue path, number 2. Black path. We have 5 miles on the ground times 200K plus 2 miles underwater times 500,000 each is going to be 1 million plus another 1 million. This is way too cheap. Is 2 million. 2 mil. $2 million to lay pipes just on this way. Now we see that the blue path is going to be 5.39 miles times, and everything is underwater. So that's going to be 500,000 for everything. And when you multiply these numbers, so 5.39 times 500 is equal to $2,695,000. So what's cheaper? Right? The first one. It's almost 700,000 cheaper. Now anyone can run these calculations, right? You're not hired for that. You're hired to optimize. Now where's the optimal route? These are two extremes. Where's the route which will minimize the cost? Well, it's somewhere over there. We want to minimize the cost of the project. You have to minimize the cost of the pipe on the ground plus the cost of pipe underwater. Now this is where you make money, right? Because as I said, anyone can compute the black and the blue. Does not involve calculus. You take a solar calculator on a sunny day, push some numbers, you're done, right? Now the red one requires calculus because we are going to run as much as calculus says so. We're going to run on the ground and then the rest goes underwater, and that's going to be guaranteed because we are using optimization to find the minimum cost. So what do I do? Minimum cost. Minimum cost. So now I'm going to call this my distance x and this my distance d. That was a good effort. So now, minimum cost is going to be x times 200,000, because that's the ground, plus distance d underwater times half a mil equals a min. And this is your objective equation because you have minimum in it. Now you have x and d that you don't know. But do not despair. Let's figure out the other equation. Is there an equation that can connect x and the d?
X plus D. X plus D. 5 minus X.
X plus d 5 minus x. Now why 5 minus x?
Well,
Because you are equaling now the red to black. I like the 5 minus x, it plays a role.
Pythagorean theorem
It's a Pythagorean theorem
in the top part.
in here, right? Now, what are the players? Well, 2 miles is a player, and what's over here on this side? 5 minus x, that's where it kicks in. 5 minus x, let me do the red. 5 minus x is the distance in there. And now I have 3 sides of a triangle, and 2 sides have x and a d. So we're good to go with our constraint equation, where 5 minus x squared plus 2 squared is d squared. So d is equal to the square root. It should be a plus minus square root, but distances are not negative, so we are ignoring the negative. It's going to be 25 minus 10x plus x squared plus 4. D equals square root of x squared minus 10x plus 29. There is your what? Constraint, right? It came from the geometry, that triangle. So, welcome to Civil Engineering 101. Do we have any takers? Yeah. Minimum distance for a bridge. Right? Oh, I go around Manhattan. The shortest route. So that you have to compute these things. All right? So now we have the constraint. So now we have 200,000 x plus 500,000 square root of x squared minus 10x plus 29 instead of the d is equal to a min, and it's ready to be hit by the, not the truck, the derivative. And now the derivative of 200,000 x is 200,000 plus, and I'm using the same trick as earlier, 2 times the square root as is, and the derivative of the argument goes on top, which is 2x minus 10, and I can cancel the 2, and it's just going to be a 5 there. Oh, this is, by the way, this is equal to a 0, right? Minimum, derivative of minimum is 0. So now I have 200,000 plus 500,000 times x minus 5 divided by the square root of x squared minus 10x plus 25 is equal to 0. Oh, it's 29, yes. It is 29. Thank you. So now I move 200,000 to the other side, divide by, right? So I have x minus 5 divided by the square root of x squared minus 10x plus 29 is equal to negative 2/5. Because all the zeros will cancel. When you move 200,000 on the other side, it becomes negative. When you divide by 500,000, all the zeros drop. You're just left with negative 2/5. So now we have equation to solve. We cross multiply to get 5x minus 25 is equal to negative 2 times the square root of x squared minus 10x plus 29. And at this point in life, we square both sides to kill the root. Now that will also kill a negative, which is great. On the left hand side, I have 25x squared minus 250x plus 625. Welcome to applied math when numbers are not 2 and 6. And on this side we have 4 times x squared minus 10x plus 29. 25x squared minus 250x plus 625 is equal to 4x squared minus 40x plus a lot, which is 120 minus 416, right? Because 4 times 30 is 120, and take away 4 because you had 1 extra. So now move everything to the left. 25x squared minus 4x squared is 21x squared minus 210x plus 500 and something. 509. 509 equals a 0. Now you go to Wolfram, Mathematica, or whatever other thing you have. You say solve 21x squared minus 210x plus 509 equal to 0. And we actually take the approximate form, we take the decimals. And we have that x is equal to 4.13 or x equals 5.87. So now we have to figure out which one of these would be the minimum, right? But these should be these guys should be optimizing, right? We have to compute the d now. We have the equation for d. D was about a year ago. This one, this square root over here. So we can calculate the value for d. X squared minus 10x. So x squared minus 10x plus 29. And we plug in 413 in it. So distance is square root of 4.13 squared minus 10 times 4.13 plus 29. And that distance is going to be what? 4.13 squared minus 41.3 plus 29, and then square root of the answer is 2.18. Or the other case, and we'll see which one gives us lower cost. That's the minimum. 5.87 squared minus 58.7 when you multiply by 10, and then plus 29, and then the square root of the answer. Okay, good, we got the same answer. So we are going to obviously kill off the 5 because you see that distance underwater is 218 on both, right? And 413 is the shorter, so you'll have less pipe. Now let's see what is the cost. The cost is going to be 4.13 times 200K plus 2.18 times half a mil $4.13 times 2, 3, 4, 5 plus 2.18 times 1,916,000. So we saved, right? The other two numbers, the black number was 2 million, and the blue number was 2,695,000, right? So these are ours. Hi.
Never mind.
So we have So do you see that we saved $84,000 with the calculation that we can just do with the simple calculator, right? Now, this one calculation that you do in an hour makes your entire salary for a year. So now all of a sudden the $50,000 bonus makes sense when you are working for the oil company, right? Because this one calculation saved, right? 84K. So these are the things that this is how money is made with optimization. You will optimize the production, you optimize the cost, you optimize the profit, you optimize, right? So you keep doing these problems, and there are entire branches of mathematics that you explore, and you are employed by the industry just to do this. This is where mathematicians make money when they're in the industry, right? So this was a problem which showed the difference, again, the path that the pipes should take to minimize the cost. And we see that that's the way to solve. Now you have similar problems and the homework, and you can practice those. I want to work out one more problem, and that's problem 37 for optimal garden. And now we're going to take a break. Now, I don't really think that people go around and figure out, all these dimensions around to optimize the garden. So let's replace garden with a pool. And all of a sudden, yeah, people do go and optimize, right? Because installing a pool is much more expensive than planting seeds to get flowers. I mean, it's all your preference, right? So we have a rectangular plot of land, and we have a pool in it. Rectangular flower garden with an area of 30 meters square. So now this is a 30 meter square pool. It's very tiny, it's a pond. You're building this for a frog. It's surrounded by grass border of 1 meter wide and 2 meters wide on sides. What dimensions of the garden minimize the combined area with the borders? So, looking for dimensions of the pool to minimize area of all. Well, the pool is in the middle, and you know what's around the pool? Concrete. So when kids run, they can scrape their knees. No running around the pool. It's a rule, right? You can relate to that? Good. So we have the concrete, right? And here is the pool, is the water. And now we need to put some dimensions to it. Now they're looking for dimensions of the pool. So we'll call those X and Y because those are our main dimensions. And immediately that should give you constraint, right? What's my constraint? It says 30 meters squared. XY equals 30, right? Meters squared is area. And you have a rectangular pool, therefore XY equals 30 is going to be constraint. And now we want to minimize the area of everything. Now area of everything goes this way, right? That's the area of everything. Question is, knowing that the inner dimensions are X and Y, what are my outer dimensions? Who's able to read technical drawings? The rest of you, not engineers. So if my inner is X, what's the outer dimension? X plus?
No, X plus 2.
Not happy.
It's
X plus 4. Because there are two sides by 2 meters each, so it's extra 4 meters, right? This much is X, and then you have a 2 over here and 2 over here. So X plus 4. How about this side? Y plus 2. Because you have 1 meter on top, 1 meter on the bottom, plus the Y in the middle. 1 plus Y plus 1 is Y plus 2. And there is your X plus 4 times Y plus 2. You want that to be minimum. Why you want that to be minimum? Saving cost on what? Concrete, right? Saving the minimum surface area, combined area is producing, right? Because your 30 meters square for the pool, that's fixed. You don't get to make the pool smaller. But changing the shape of the pool is going to change the shape of the rectangle around to minimize the area of the, right? So minimum surface area would be the minimum amount of concrete that you have to pool around. I really don't know why they go with the optimal garden and stuff like that, because no one does that. You're just planting grass and stuff. That stuff is cheap, right? Try pouring concrete around the pool, see how well that goes, right? It's expensive stuff, right? Tens of thousands of dollars to install the pool. Not 6, or seeds. And toss, right? Like, wow, amazing. Good. Guys, you have your equations. Solve for x or y. You see that it's symmetric, it doesn't matter. Plug in the bottom equation, hit it with the derivative. Well, multiply it out first. Hit it with the derivative, and see what we get. So y equals 30 over x. Plug in. I love these problems. They're so cool. X plus 4 times 30 over x plus 2 equals them in. Multiply. And once you simplify, hit that with the derivative, and then calculate x. Let's go. Now square root of 240, right, should have positive and negative answer. We are only going to keep the positive because we are interested in distances. Am I doing this right?
2 and 120 should be opposite. Anyway.
So,
60, I think.
Yeah.
Because the
Multiply by 2 and 55, but
so which over here?
no, the
no,
bottom.
bottom.
120 over x squared equals 2.
1, oh,
1 over x squared equals 2 over 120, so flip it.
oh, no. Yes, so this is 60.
Yeah.
Oh, whew, okay. So what's the square root of 60? We need decimals because we're working with concrete.
7.75.
How much? 7.75. Thank you. We're working with the concrete here, so the square root of 15 won't cut it. No, even the iPhone can do it. If you flip it on the side, they figured it out that they can add. I didn't bash on Apple at all today. This is why I'm miserable, actually. Yeah.
Let's just compliment it.
Yeah, it was. Yeah, I tried. Yeah.
Oh, that's true.
Yeah, right.
We had this math conference on a Saturday, and few people were so proud owning Macs and so on, and they did not appreciate my because it was an issue of displaying something on a projector. They had the connector and everything, right? They were connected, right? It's just not displaying. And I said it would be so much easier if you had the real computer. I was like, "What do you mean? This is Mac." I said, "Exactly." It's like, "You don't like Macs?" I said, "Is that obvious? Look at my face." 30 divided by 7.75. 3.87. All right. So dimensions of the pool, and this is in meters. Yeah, this is not good for the pool. I am 2 meters tall, so 7 meters is up to the
It's one of those exercise pools that they show on TV where it's like
for physical therapy, not for swimming. Okay, all right, sure, all right, fine. Yeah, we could go with a jacuzzi, right? That's
or that.
so. These are the dimensions of the pool or the flower garden, right? That will minimize the amount of concrete around. All right, so let's take a break. When we come back, we are going to do some linear approximations, and guys, that's the stuff that you will actually be using to calculate things in life, which will be upgraded in Calc 2 to the higher, more efficient way of computation, and then in Calc 3 in the multi-dimensional with the tangent planes and stuff like that. So next lecture will be really cool.